stand corrected. Question about homework 2. Nada. Remind me?
Second question from the assignment 2.
Which asks?
The closest pair of triangles.
Yeah. Yeah. Okay. And the question? I mean, I kind of said it in the, I kind of mentioned it in the comments. I don't know that the smallest perimeter triangle will use as an edge the shortest edge. So that's wrong. The shortest edge might appear somewhere here, and the shortest perimeter might appear here. So I cannot use this algorithm as a black box. But I can definitely take ideas from this algorithm. That's a big hint. That is, I'm looking at the code and ask how does the closest pair works. I'm adding one point at a time. And when I have a point, then I'm checking what, if this new point, pi plus 1, is a part of a new pair, then who is the other point in the new pair? There are several candidates, but you can show like everybody that is not very far from pi plus 1 is a candidate, namely 2 block cells for each direction is all you need to go. And then you're counting how many points I have in all these block cells, grid cells. And when you're summing all of them, you realize that in each cell there could be at most 1 point, so there could be at most 25 other candidates with pi plus 1 that I need to check. That's for the closest pair. Now you're adding pi plus 1, which is part of a triangle. Where are the other vertices of possible triangles? How many points in a grid cell? How many? A lot of the things needs to have this algorithm. This algorithm has a lot of analogy in it. Otherwise, it would have made it. But without fully understand this algorithm, this is a really hard question. And if you do fully understand this algorithm, then it's trivial, pretty much.
Verify the triangle property as well for this question. Like the two sides of the triangle should be greater than equal to the third side of the triangle.
You need to, there is a chance, I'm not sure that I answer your question, but there is a chance that there is several, with pi plus 1, there could be various other triangles that it participates in, and you need to check that this is a, it's not approximation, it's not roughly. It is the smallest perimeter triangle. But if you really wonder how many other triangles do I need to check, yeah, play with this. OK, skip lists. You said that you know. I'll mention it once again to refresh your memory. Starting from the very top, I'm looking for an element x. I'll be careful not to reach x itself if I also want to do insert or delete. If I just want to find if x exists or not, then I can reach x directly. Let's say in this case, I'm careful not to pass via x. And the idea is that at every level, I'm trying to jump as far as I could in this particular level. So always start my search at the very top, see that it's safe to jump over to 21 because there could be a lot of keys that I'm jumping over, but all of them are smaller or equal than 21, while I am trying to find one of these two numbers, right? So safe to jump from here, safe to jump from here. Next element too large, telling me go down. And now you have a smaller refinement, smaller details of each jump, but still safe to jump to the next element because still smaller than either of these two down. And that's where my search ends if I'm careful to stop at the predecessor, right? I see here that when I'm looking for 116, next element is too large, so I cannot jump to it, larger than 116. and I'm going to see if I can go down. That's what happened in this line. If P down is null, and I found P's and return. OK. I want to, and I'm asking you on the homework, so to understand the big properties of the skip list, let's talk about a perfect skip list. Perfect skip list is my terminology. By the way, a very good description of skip list you'll find in the Dennenberg and Lewis textbooks that I mentioned on data structure. The one that I said that you should go and either download it or buy a used copy. They are going for, I saw them used for less than $10. And it's a fantastic book. The Dennenberg and Lewis data structures, algorithm. Data structures, no algorithm. But I want to introduce you to a perfect skip list that is my terminology. I've not seen it in any other book. That goes as follows. As usual, it's a skip list where all the keys are in the lowermost level. All the keys are in the lowermost level, like any other normal skip list. But now, every second key appears in level 2. OK? So here there is nothing. This is a deterministic description of the data structure. Every second key of level 1 appears in level 2. Right? And every second element from level 2 appeared in level 3. Remember that when we look at the levels, it's a set of keys per level. If ki are the keys, the set of keys in level I, then it's always true that K1 is a larger set, contains all the keys. And now K2 is a subset of the keys of K1. And K3 is a subset of the keys of K2. That was, and so on. As many levels as you can. You're right. If you're in level 3, then you must be also in level 2, and you must be in level 1. Perfect skip list will say that when I decide whether or not to promote a key, each key starts at level 1 and possibly being promoted. When I start whether or not to promote a key, the rule would be yes, no, yes, no, yes, no, alternating. Promoted, not promoted. Promoted, not promoted. And so on and so forth. And the same rule applies for level 3. How do I create level 3? I look at level 2 and do the promoted, not promoted once again. Promoted, not promoted, promoted, not promoted, and so on. And of course, after log n levels, I'm done. What? Since I divide by 2 the number of keys at every level, after exactly log 2 levels, I'm done. I'm either to 2 or 3 keys, and I don't have anything to halve. And everything is deterministic. And it's kind of worth mentioning the perfect skip list, because there are a question about it in the homework. Homework, what used to be, homework overachieving 3. So it appears in the homework. A very typical question that I can ask in the midterm would be, what will be the parameters of a skip list if I'll tell you that the rule is yes, yes, no, to promote. That is yes, yes, no, to promote. That is, this will be promoted, this will be promoted, this will not. This will be yes, yes, and no, and so on. Right. I can ask similar question, just that I'm, or alternatively, no, no, yes, no, no, yes, no, no, yes, no, no. Every third element being promoted. So then I waste less memory, but the search time will increase. It's similar exercise. I'll add it to the homework quiz. No great. It's similar exercise that if you solve the questions for the dynamic arrays, you'll see how the same type of math appears here. Actually, exactly the same math. So that's another reason to use perfect skip list. And the third reason is that sometimes if you have a skip list, which is randomized data structure, and it doesn't work well, it's not well balanced for the real skip list that is randomized, and you have a few seconds to maintain all the structures and take all the keys and build a perfect skip list for them. And I ask you to show in the homework, but it's trivial to show that you can do it in n log n time. Okay. And here I'm just demonstrating that I can do the find operation. And in the perfect skip list, it's easier to understand what the search time of the find operation that is a bit trickier on the real skip list. Okay, real as opposed to the perfect. I mean, the real will be deterministic. What would be the search time of when I'm looking for a key in the perfect skip list? Then what is the search time? Obviously, there are log n levels. But the saddle argument is that in each level, I will visit either 2 elements, possibly I'll visit 1 element, really I visit, depending what I call visit. If I came from down, maybe when I'm coming from the top, maybe I'll just go down another step or visit 1 element, but I will not visit 3 elements from each level. There is no level that I'll visit 3 elements. Why? I'm doing a search operation, find operation. I'm following my path in the skip list, and I want to convince you that in none of the levels, there is no chance that you'll check 3 keys. You might check 1, you might check 2.
Number 3 will be on the upper level.
If I'm visiting, had I check 3 elements from the same level during my search, then one of them also participates in 1 level up, level 3 in this case. And if it participates in level 3 and I check it, it means that it's smaller than x, the elements I'm after. And the code said stay in 1 level as long as you could. So you would have visited this element once again. You'll see the proof in more details coming up, but that's already a clean way to explain why it's exactly log n, log to the base 2 of n time to find an element in a perfect skip list. Right? You will not, there are log n many levels, and in each one you'll spend at most 3 keys, or check 3 keys, visit only 2 keys. Constant number of keys per level. Okay. A point that people tend to ask at some point or another, if I'm searching for a key and I found it in level 4, should I stop the search or not? Looking for 71, I found it in level 4. Should I stop the search or not? And the answer is that depending what's your purposes. If your purpose is just to ask, is there a student whose ID is 74, you can stop it right here. If your purpose is to ask what are the details, the record of the student whose ID is 71, then you don't save it 4 times, both because it's waste of memory and, more important, redundancy. As you all know, there are terrible things that can happen to you if you start updating the record of student 71 and you update it in some of the places, but you crashed and you didn't update the other. You want to store the details only once. So where will you store it? Probably in the lowermost level, possibly in other hard drive, and there is a link from this point to this place. So in this case, you need to visit all the way down. So depending on these details, you might need to go all the way down or not. Right. Make sense? I think. OK. So what's the algorithm for inserting new keys? And I want to remind you, if that looks complicated, I want to remind you that you didn't have to implement it, at least not in this course. But even in the splay trees that were very simple, we still had the case of rotations of the zig rotation, zig, zag, zig, zag. 4 types of rotations if the key have a grandparent, 2 types of rotation if the key has only one parent but not grandparent. Lots and lots of checks and ifs. I want to show you, as in contrast, how simple it is to do it in a skip list. So, first thing, I want to insert a new x, new key. I want to determine this magic number k. K is in how many levels x is going to participate. Because obviously I want to balance my keys somehow. I want that every once in a while there will be a new element that participate in large K. So frequently I want an element that participate in only these many levels. So the secret in determining, when I'm inserting x, what is a good balance, or basically to determine K, in how many levels this new element is going to participate. Let's assume that this is done. Now I perform find x. Perform find x, but I keep track of this insertion path. And now, and that I showed you at the beginning of this lecture, how to do insert in a sorted linked list. Again, at the beginning of this lecture, I revised stuff that you know from many years ago, how to perform an insertion in a singly connected, sorted list, not a skip list, just one linked list. What are we doing in the skip list after I found x? In each one of the levels, do just insert in of the new elements as if it is just normal, singly connected, sorted linked list. You found the elements before the new guy. You're updating its next pointer to point to the new guy, right? And just point between the, here I decided in this example that k equals 2, so 119 is going to be in 2 levels. In this level I insert it, in this level I insert it, just making sure to update it down. And the way it affects each level is just that the next goes to point to the next of the new element, and the next of the new element goes to point to what the next of the new guy is going to point to what the next of the previous element used to point to. Infinity in this case. But nothing tricky in it. K, that was inserting of 119, and I decided that k equal to, it's going to participate in 2 levels. It's possible that k will be larger than the current existing number of levels. And in this case, I need to open a new level. K is 4, I used to have 3, generate a new guy. Generate a new level, generate a new level, and obviously this new level contains as any other level, minus infinity, infinity, and the new guy. And of course, top needs to be updated. Okay, here is how I decide what is k. I need a coin for this experiment, and I'll decide that k equal 1. And I'll toss the coin, and if k, I'll toss the coin, and if so k equal 1, and I'll toss the coin, and if it happens to be face, then you're doing 2 things. You are performing k plus plus, and go to do it once again. And the moment that you got a tail, then you stop increment k. So as long as my coin shows a face, I keep incrementing k, and each time that I increment k, I also toss a coin once again. By the way, you all know this Google question. there is you and you and you. I want to pick one of you where each one of you has exactly 33 chance to be picked, 3 people with a coin. How do we do it? It's a cute puzzle. With a coin, assume perfectly balanced coin, perfectly fair coin, I want to pick between 3 people. I toss two times, and then
Yeah, I forgot the last half, but yeah, maybe we could check it. Got multiple times.
don't you want to work in Google? Sorry?
3 times?
You're tossing yes and no. You're tossing 2 times. If it's face, it's you. If it's face, tails, it's you. If it's tail, face, it's you. And if it's tail, tails, then I repeat. But then the running time might be infinite. The expected running time is only 2. The expected length of the running time is 2. It is, on average, you'll do 2 expectations, but in the worst case, you'll continue forever. But once you decide about a winner, it's a done deal. Right? And it's exactly the same probability of each one of the 3. OK, back to this case. If everybody understood my analogy with a coin, how do I do it in my computer? One pseudocode that I suggested, you're picking a random number between 0 and between that is either 0 or 1 with probability half and half. At the homework, I don't think that I ask you, but you do want to check what happens if the probability is, say, 70-20. It would be similar to what we did with a skip list, 70-30. Or any other probability. Here, my probability is exactly 50-50. And I'll keep doing the while as long as I got 1 over here. And in each iteration, I increment k. And it's very, very surprising that it works. A, because it's so simple. B, because I don't care at all about how the skip list looks like or where x, the new element, is in the skip list. It's exactly the same code no matter how many keys do I have, no matter where x is in the beginning or the end of the skip list, how many elements do I have. It's really ridiculously simple to implement, and that's why it's also so fast code to run. There is barely any ifs. I determine what is k, and then going back to my insertions, going back 1 slide, and do 1 insertion when I know it how many levels k participates. OK. And that's the whole algorithm for insertion. Deletion, if you remember a binary balance tree, AVL, splay, redneck, all these trees, 2 3s, all these trees, if I wanted to delete x and x was here, then, well, not in splay, but in AVL or just binary trees, I wanted to replace x with some leaf that was somewhere over here, like the predecessor element, and then I can finally eliminate x. And possibly then I need to do some rotation to balance x, because now the balancing properties. Here's how I delete an element from the skip list. Find it and get rid of it. How do I get rid of it? The same way that you're getting rid of an element in a normal linked list. That is, I decided that I want to delete 71. I found the predecessor element and take the next of the predecessor to points to the next of the to be executed element, the 71. I look at its next, looking at previous 1 element, and points to this guy. Right? As simple as it sounds, really, there is no hidden details. If because of it the top level becomes empty after the deletion, then you're getting rid of the top level. And if then the new top level is also empty, get rid of it too. OK. So the expected number of elements in the skip list is n. And here I'll use the whiteboard to give a bit more of a rigorous proof. I didn't update the slide to have it. First, how many keys do I have in the perfect skip list? Let's go over the keys in the perfect skip list. In the perfect skip list, and in the lowermost level, one for the lowermost level. One level above it, there would be. So, which is 2. I told you that we'll see this sum all over the place. Right? And sure, I'll actually stop after log n levels, but who cares? I might as well continue, but because so that's an upper bound. Actually, I need to stop somewhere, but even if I add this minusculous element, it still sums up to 2. OK, what happens in the real skip list? As you all know, yij is a random variable which is 1 if xi participates in level j. You know, before I use this definition, let's see the hand wave, the non-formal algorithm. What is the I do have this slide. I do have this slide. Sorry, we don't need it. So, first, hand wave proof. What is the probability what is the probability that xi participates in level j? First, it doesn't depend, each element, it's completely fairness between the elements. Every element has the same chance to be in level 1 or level 2 or level 3. The way that when I inserted xi, I had to decide what is k for this element, and I didn't care at all what's the value of xi. Right? So it's the same for every element. Now, what is the process that I decide about an element? To participate in level 1, let's check. For j equal 1, to participate in level 1, what's the probability that xi to participate? By the way, don't confuse here between xi is a key. I mean, the same keys can be stored in multiple levels. It's the number of elements, the number of disks that you saw in the skip list. But in level 1, this probability is 100%. Everybody is in level 1. J equal 2, this probability is half. Level 3, the complicated way to think about it is as a conditional probability. You are in level 3 only if you made it to level 2, so what's the chance times that? Well, it's simple. To be in level 3, you need to win 2 coin toss. Right? The same way that we had earlier. The first coin toss should be, for you, should be face. The second one should be face as well. Probability for this is half. Is half, so is half times half. You need to win the 2 coin toss, so it's 1 times half, writing it as 1 over 2 to the 1 to the Jew, 2 to, yeah, right. And for arbitrary j, this probability is 1 over 2 to the j minus 1. a bit noise because the lowest level is level 1. So here is an intuition to where we are going, also in the real skip list, the randomized one. The expected number of elements, and here I'll use expected very loosely. I expect all the elements to be in level 1. I have a slide for it, actually. Sorry. It's an approximation of a proof. Right? I expect all the elements to be in level n. I expect, because of these probabilities, half of them to be in level 2. Right? Kind of law of big numbers. If n is really large, each one has a probability of half and half. So that is the expected number of elements in level 2. Now, to ask how many elements are in level 3, again, I can ask from this subset, that I'm not sure what its size, what the probability is that you are going to this subset. That will be really hard to calculate. Much easier to ask what's the probability of an element to go to level 3, quarter. So out of all the starter, have quarter of the elements to make it to level 3, and so on. That's the total number of elements. After log n many levels, you run out of keys as a hand wave. And so the total number of elements altogether will be, again, with this hand waving, would be n plus n half plus n over 2 plus n over 8, what we just saw, which is 2n, just like the perfect skip list. OK, so let's do it more accurately. So it's not yi, it's, let's call it xij. Not xij denote a random variable, which is 1 if the key ki participate in level j. In level L, it's bad font. xil is a participate. xil is a participate that xi participate in level j. If and only if xi participate in level L. Okay. Now, how many elements do I have in the skip list right now with all the randomness? Let's say that I already make all the coin toys. I inserted all my elements. How many elements do I have right now? Well, you get 1 for each value, which is 1. That's, you need to allocate a cell in this case. And if xij, xil is 0, then you don't need to waste any elements because this key didn't make it so high. OK. We finally have a client on Zoom. Can you hear me? Can you hear me on Zoom? Oh, OK. Everybody feels convenient that this sum, what do I sum here? I run over all the keys. I goes from 1 to n. I go over all the elements, and I look at xil. Sigma over I goes from 1 to n. Sigma over from L for level, from 1 into whatever the max level is that I'm using right now, max level is, of xil. That's exactly how much memory, how many cells I have. You're spending one per each cell in the skip list right now. There is no randomness yet. That's for one concrete skip list. If each one of the keys, going back a bit, if each one of the keys made it to the maximum level, then for every xi, you're getting 1 per each level that this key participates, maybe all the way up, whatever many levels, right? So this is exactly the number of cells. This is exactly how many cells you have in the skip list right now. We are doing a similar exercise with the random variables now in the third, fourth time. By the way, I can refer you to a few books that do randomized analysis, randomized algorithms, if you want to see it written by other people. But everybody understand where we are going in general? We want to sum up the running time usually. In this case, it's a memory requirement. So we are just saying for every element in the memory requirement, we'll assign a random variable, which is a scary element. Remember, we called it a variable, but it's actually a function of something. Did this element participate or not participate? So it's not a variable that we have to decide upon, but it's completely determined once we decide how the skip list looks like. It's a flag that is on and off. I don't like the term variable here. It's a function of how the skip list looks like, and this function is a Boolean one, true or false. Did the ith key made it all the way to level L, or did it not make it to level L? And you sum it up for all the levels and all the keys, and that's exactly how many cells you have. So far, so good? Everybody, if you lose me, from now on, it's just a standard gymnastic we did several times. But that's a point that if you still don't feel comfortable with randomized analysis, that's a point where you should probably, that you have the highest chance to get confused. So I'm happy to spend more time if somebody doesn't feel comfortable with this big attack of multiple random variables. Nobody says anything, so let's continue. Now I want to ask, what is the expected? I think that it's readable enough. I want to ask, not in one concrete skip list, but I'm doing the experiment a million times. What is the experiment? Take the same set of keys, create a skip list for them. Each time you're tossing the coins, but every time that you're doing your experiment, obviously your coin might give you a different way, unless you are zeroing your seed of the random variable to the same value, and then in all the experiments you'll get exactly the same behavior. But if you know not to use the same seed, then each experiment, the skip list, even though the keys are the same, how the skip list looks like is completely random. So after every time that I constructed the skip list, I count how many keys, how many cells do I have, which is exactly this expression, and I'm doing it a million times. And I want to ask what is the average number of elements in the skip list. What is the expected value that I'll get if I'll repeat this experiment a million times? OK. And here I'm using our instinctive uncontrollable reflex. Every time that I see expected value of x plus y, I immediately write it as e of x plus e of y. That's extremely helpful. It works if they depend on each other. If they don't depend on each other, I don't care. It's still true. So now when I ask what is the expected value of the overall number of elements, repeat the same experiment multiple times, it is just the same sum, the same double sum of the expected value of xi comma L. OK. And now I'm using the second trick that we saw with random variables when they are Boolean random variables, 0 and 1. Then what is the expected value of xi? It's 0 times the probability that it's 0, plus 1 times the probability that it's 1. So we just care that this number is nothing but E of xi comma L is nothing but the probability that xi L equals 1, which is, to state it in words, which is just the probability that ki participates, was promoted all the way to level L at least, maybe more. I'm not saying that it doesn't participate, that that's the highest level of this key, by the way. I'm just saying it participates. Maybe it participates in more levels. Ki participates in level L, which is, this discussion just told us that this is just 1 over 2 to the L minus 1, right? Because we sum in level 1, so in level 1, this probability is 100%. So the only thing that is left from this big monster is that when I do the summation, that I'm summing from I goes from 1 to n of sigma of 1 over 2 to the L minus 1. L starts from 1, and let's make it even small or equal, and replace it by go to infinity. Obviously, I'm just adding elements to go all the way to infinity. What's written here? You all know what's written here. It's 1 plus half plus a quarter. This is 2. And I sum 2 n times. Sigma of 2i goes from 1 to n of 2, which is 2n. OK, and that's no hand. There is no hand waves over here. OK, for these theorems, I will hand wave a bit to argue this theorem. Maybe I'll ask you to go over it in more details. But the expected time per insert or delete is order of log n. Insert, delete, find. And why is it? So first I want to convince you that when I'm doing an insert or delete, as opposed to completely in contrast to binary search tree, where once you found the element, then all the hard work is happening because you have to rotate and bring this element to be a leaf and decide which of the 3 cases of delete. Here, the bulk of the work is that I start from the top level, and I go to the right, goes to the right, go to the right, go to the right, go down. Go to the right, goes to the right, goes to the right, go down, and so on. And then possibly at the end of the work, I'll decide that maybe that this link and this link and maybe these pointers should be updated. Maybe this one as well during deletion operation. Just the opposite of insertions, but that's just constant time per level. These updates that I'm doing are just constant time per level. So once I convince you that there are log n levels, then obviously the number of updates in each level, that is 1, or the total time for updates of levels is 1 per level. So that's not where the bulk of the work is. The bulk of the work is to do the find, because in a find operation, there is a chance that in the same level I'm spending a lot of time. There is no other. In the perfect skip list, I knew that in one level I will not spend more than 3 keys of the same level. Here I'm all in the mercy of how was my karma when I tossed the coin. So I will not prove to you that it's impossible that you'll spend a lot of time per level, possibly n time. I'll just try to convince you that it's very unlikely. And later on, we'll try to formalize more what do I mean by saying unlikely. So let's pick one of the levels. Let's say that's level r+1. Maybe it's a top level. And in level r+1, from level r+1, I went down into level r. Maybe now I'm in the lowermost level. And in level r, I spent a lot of time. Right? I'm trying to convince you that it's unlikely. It's unlikely that in level r, I'll have to visit many elements. But let's assume that I did. So in level r, I visited b1, b2, b all the way up to b8. When I'm doing find or delete or insert of x, why did I check all these elements? I'm absolutely sure that they are all smaller than x. Why? Because I scanned forward. If I reached one of them that is larger than x, I would go down or report that I found whatever I'm looking for. So all these guys are small or equal than x. Look at this element c. Smaller or larger than x? Larger, because that's the reason that I went down. C is larger than x, for sure. Now, is there any chance that any of these elements that made it, it's nice achievement, they all made it all the way to level r, whatever r is. Any chance that any of them make it also to level r+1, b2, b3, b4, b5? Any chance that any of them make it also to level r+1? Could b5 also be in level r+1? In general, yes, but not if this is my search, because I know that b5 is smaller than x. Had it been also participating in level r+1, then my search wouldn't go from b down to b1. It would have jumped to b5 because it's smaller than x. Conclusion, and it's a hand wave, but it's conclusion. b2, I inserted it. I tossed coins, and b2 made it all the way to level r. Again, I don't care what is r. R might be level 1, but it made it all the way to level 1, got promoted to level 1. And then we toss the coin, said, hey, will you be promoted to level r+1? And the answer was no. That's why you stayed. That's the highest level for b2. That's also the highest level of all the elements up to b8. Now we can ask, what's the probability that you toss a coin 8 times in a row and you will not have any face when you're tossing the coins? 8 points, and that's because there are 7 elements that I all scanned. This probability is 1/2 to the 7. So go on. It's not a proof that I'm spending a constant time, but it's a proof that the probability is that in the same level during the search, I'm spending many elements, goes down exponentially with how many elements I'm checking in this level. Okay? It's unlikely that if you are spending many elements, if you're scanning many elements during the search, you're scanning many elements in the same level, it means that none of these elements make it to the next level, which is quite unlikely. How unlikely? Each one of them did not make it to the next level with probability half. Probability that neither of them make it to the next level is half times half times half times half. They all have their chance. So it's 1/2 to the number of elements that you're asking. So that tells you what the probability is that you will spend 8 elements in one of the levels. What the probability is that you'll spend, that you'll visit 9 elements, that you'll visit 10 elements, you'll visit 11 elements. These probabilities going down so quickly, so nicely, kindly, they go down exponentially. So the average number of elements that you are visiting, the expected value, is only 2 or 3. Makes sense? But it's only a hand wave of why are we not expecting to see long strips of elements during our find. Again, I'm not saying anything about what I'm doing after finding x, or after finding element larger than x. Possibly later on I'm going down levels. Possibly before that I scanned many levels. Let's just try to ask how many, in the same level in level R, how many elements do I have to scan during the find? And I try to convince you that it's unlikely that you scan many of them, more than a constant. Now, to put it all together, remember there are log n levels with high probability, log n levels with high probability. In each one of them, I scanned about 7 elements with high probability. So all in all, the find takes log n with high probability. And the insert and delete takes find, which is a bulk of the time, plus a bit update that takes much less time. OK? So that was about the time for insert, delete, find. Are we good? Questions? OK. Let's try to, out of all the parameters, I wanted to become more rigorous on one of them. And I asked, people sometimes ask me, we studied that we can limit the maximum level to be log n or so. And in my code, if you saw, I didn't try to limit what is a maximum k. It's a big bug, for example. And I'm using it more as an exercise to show you a very light version of Chernoff bound. Chernoff bound in general asks something along the line of, I have some random variables, x1, x2, xn. I'm looking at the expected value of the sum I'm looking at the expected value of the sum of the xi in some very simple version of Chernoff bound, and I'm asking what is the probability that I'll have a case where the sum of the xi, in one of the experiments that I'm doing right now, I'm building one concrete skip list, say. What is it likely or is it unlikely that the sum of values that I'm getting will be far, far away than the expected value? Okay, and there is various parts about it, or various form about it, depending on what are the random variables and which forms, and it all goes down into Chernoff bound. I hope that I don't spell it correctly. Maybe I'll ask something along it in the homework. Now I'm going to show you an example of Chernoff bound that tries to limit this probability without using any Chernoff bound directly. It will be completely, fully explained in what we are going right now. So out of all the random parameters that we had in the skip list, one was really how much time the search takes. One was how many levels, how much time, what is the maximum gap between two elements in the same level. I can pick many parameters. Here is one that I thought that is really simple and easy to understand. Let's look at the height of the skip list. Height of the skip list is just how many levels do I have right now that are, of course, I don't have any empty levels. If the uppermost level is empty, I delete it. So what would be the average number of levels? We hand wave about it. We said in the lowest level, I have n. Level above it, I have n half. Level above it, n over 4. So it makes sense that after log n, log to the base 2 of n many levels, I'm running out of elements. But it's completely hand wave. Let's try to be more formal. Log n we are expecting to find. So obviously, n is larger, more levels. Makes sense that we'll find more levels. But so I cannot prove that you'll never see a skip list that is more than log n levels. But I can ask what the probability is that you'll see a skip list that has 2 times log n, or 3 times log n, or 4 times log n. So the unit that I'm counting is how many times log n you'll see in the skip list and what's the chance that it happens. Okay, that's going to be quite simple. Everybody agrees that, everybody understands at least what I'm going to examine. What's the chance that you'll see a skip list that has these many levels, that is, or these many levels, or this, or this, for a given n. And before that, I want to ask you, I'll draw on the whiteboard 2 targets. One I'll call A, one I'll call B. I'll toss a dart, and if the dart happens to hit the target A, then I'll say that the event A happens. My dart hits the area A. If my dart hits B, I'll say event B happens, and I'm asking what is the probability that either A happens or B happens. And there is a formula for it, right? This is the probability that A happens plus the probability that B happens, which is just the, why did this come from? Because if the area of this guy is 1 by 1, then the chance that I know that I hit this square, then the chance that I also hit A is just the area of A. Right? So the chance that I hit A is just the area of A, plus the probability that B happens. But now you see that I double counted this area twice, so minus something. Minus, let's write it, the probability that A and B happens. Camera will not see it here, minus the probability that A and B happens, that I hit here in the intersection. Because when I counted the sum of the areas of this plus this, the area here in the middle was counted twice. So you all know it. But this formula will turn out to be way too complicated for us. Why? Because we don't have only 2 events, we will have n events. And when I have even 3 events, and I ask what is the area of the union, but I want to ask basically if I hit either A or B, what I'm asking here, sorry, I went too far. What I'm asking here is, if the square is 1 by 1, what is the area of this shape, the union of 2 of them? And this is just formula of this area. If I have 3 shapes, that's become quite a nightmare, because now it's the sum of the probabilities of A, B, and C, minus the probability of pairs, plus the probability of triples, and so on. So I don't want to use this formula exactly. I just want to say this number is this plus this minus a positive number. So this number is large or equal than probability of A plus probability of B. Point. Why? Because what's the difference between this and this? Here I subtract something positive. Then, wait. The other way, wait. Here I don't subtract. This is something positive that I do subtract, something here. So this should be larger. Where am I going with this? I'm going with this that this number is going to be so tiny that which will imply that this number is going to be tiny as well. Okay, so let's just repeat these probabilities. Can check it, nothing more than what I just hand wave and played a bit with probabilities if that's the first time that you saw probabilities. Let's get back to our skip list. If the height of the skip list is t, it means that one of the elements, at least one, wants to be in this level. When we toss the coins for this particular element, at least one of them made it all the way to level t. If the height of the skip list is t, then one of the keys decided I want to be in level t. If all the elements want to be in level less than t, then the height of the skip list is less than t. So let's pick some number, k. How could it be that the height of the skip list is more than k? Possibly x1 decided that it wants to be in k or more levels. Possibly x1, or the first key, k1, wants to be in so many levels. I'm just using k here, so let's move to, the keys are x1, x2, xn. And now the key x1 wants to be in so many levels. Possibly that's the reason that the height of the skip list is so tall. Or possibly x2 wants to be in so many levels. And it's logic, all right? It could be that both of them wants to be in so many levels. Or x3 wants to be in so many levels, or up to the last element that wants to be in so many levels, in log n levels. And it's enough that one of them wants to be, but it will be the same thing if I have more of them. Now, this will be an event in my book. An event, x1 decides to be annoying, wants to be in 10 log n many levels. That's what would be k. Way too many levels. It tossed the coins and it made it all the way to so many levels. What's the probability that x1 made it to level k? We played with this. To level k or more, 1 over 2 to the k. I ignore the -1 here just, to keep the expression clean. It's actually k 2 to the k -1. Let's just write 2 to the k. Because the k -1 will not have any impact. What's the probability that x2 make it in so many levels? Same thing. All the way up to probability that xn make it to too many levels, 1 over 2 to the k. Now, what's the probability that the skip list has so many levels, has k levels? It's enough that one of them wants to be in this case. It's either the first one or the second one or both. That is, A will be for x1 for the first key, B will be for the second one, C will be for the third one, D will be for the fourth one. There are a sequence of events. What's the probability that any of them happens? The or, this expression, that my dart hits at least one of them. One of the keys decided to be that annoying, at least one of the keys decided to be that annoying that it wants to be so tall. So what did we say about the probability of the or of events, of the union of events? That it's small or equal. That's why I use such a large font. It's not exact value. It's not even approximate. It's small or equal than the probability that only x1 decided to be, plus the probability that x2. Even though it could be that these events might or might not be dependent on each other, I don't care. All the way up to the probability that xn, and I just sum up all these numbers. So altogether, I got summing up n times 2 to the k. It's n divided n times 1 over 2 to the k. Once for x1, once for x2, one all the way up to xn, n times 2 to the k. That's a probability that any of the elements, possibly one, possibly more, made it all the way to level k. And I don't care at all what is k. Now, obviously, if just to clear some possible confusion, what's the meaning of this formula? If k equal 1, then all that is that the probability that any of the elements the side to be in level 1 is n times half, which is much larger than 1. It is a mistake to talk about that the probability as a probability as n half. No, because it's small or equal. Probability is between 0 and 1. But just in the case of k equal 1, sorry, it's not a very meaningful. It's like to say you are in a balloon. It's a correct answer, it just doesn't give you any more information. And I'm not going to repeat this joke. It wasn't fun even in the first time. But the n over, that this number might be n or larger than 1, is fine. It's still correct. It just doesn't give you any information because presumably this probability is smaller than 1, and I bound it by some huge number. Who cares? But it will be interesting when I'll take numbers that are a bit larger, k that is a bit larger. Right? So now, what is the probability that any of the keys xi is participating in this level? It's, as we proved, it's smaller or equal than n times 2 to the minus k, 1 over 2 to the k. And again, I ignore the plus 1. Now, just to remind you, if I have any numbers y, a, and b, then y to the power of a times b is just y to the power of a, all of it to the power of b. Or I can switch the a and b. It's also y to the power of b to the power of a. What is 2 to the power of log 2 of n? It is just a complicated way to write n. Right? 2 to the power of log 2 of n is just a complicated way to write n. Because log just asks me to which exponent should you put as the exponent of 2, so you'll get n back. That's the definition of log. What is 2 to the power of 5 times log n? I'll switch the 5, the a and b. I'll switch the order. It will be 2 to the power of log n, 2 to the power of log n, all of it to the power of 5. So it's just n to the 5. And there is nothing, people start to look desperate, and it's really not. There is nothing complicated here. So what I said so far was true for any level k. But let's see when does it have any teeth. So I'll write k equals z, another variable, times log to the base 2 of n. Why? I remind you, I want to ask what is the probability I want to ask what is the probability that the height is larger than 2 log n? What is the probability that the height is larger or equal than 3 log n? Right? Log n is a normal. What's the probability that it's twice the normal? What's the probability that it's 3 times, 4 times, 5 times the normal? So this number 2, 3, 4, 5, 6, I'll call it z. And then I'll write k from here. K from here, I'll just write it as z to the z times log base 2 of n. Do you think about it as this integer 2, 3, 4, 5, 6? So what is 2 to the power of k? 2 to the power of k, what did I say? I replaced k by z log n. K was z times log to the log 2 of n. So 2 to the power k is 2 to the power of log n times z. 2 to the power of log n is just n. 2 to the log n is just n to the power z. Z will be 2, 3, 4, 5, 6. So why do I do all this exercise? Because the probability that a skip list has more than k level is n. I need to cancel somehow to get rid of this n over here that destroys my calculation. So I want to have the thing in the denominator. I want to express it not in terms of 2, but in terms of n as well. So I can make sense of all these expressions. There are too many variables going on here. So the probability of seeing a skip list with more than z times log n many levels is less or equal than n divided by 2 to the k. What is 2 to the k? It's 2 to the k is 2 to the z log n, which is n to the z. So this is just n divided by 2 to the k, which is n divided by n to the z, which is 1 over n to the z minus 1. But here I have n to the z, here I have n, the 1 of the z's cancel each other. You're left with 1 over n to the z minus 1. And that's exactly where I wanted to get. So I looked at this very generous formula to add sums, which was definitely overshooting, but I'm still getting, because of this formula, a very manageable and very simple expression. And it definitely has teeth, because now it says that that's a probability that you'll see a skip list with n keys, and its height is z times log n. Let's take some examples. It's too abstract. Let's take some examples. N, number of keys, not too large, 1,000. Notice that everything that I'll say will be even stronger the stronger n is. Z, let's take z to be 7. I'm asking what the probability of seeing a skip list with c with 7 log n many levels. The probability that this happens would be small log of 1,000 is what we expect to find. That's the average. Sometimes, because of randomness, we'll see taller skip list, maybe 2 log n, maybe 3 log n. Is it likely to see a skip list with 7 log n, log 1,000 many keys? The probability that this happens is smaller than 1 over n to the z. N is 1,000, z is 7, 7 minus 1, 6, 1 over 1,000 to the 6. So extremely small. You still call it too fast because your job depends on it, I don't know. You want to say that's still too large number. Let's replace z equal 7 with z equal 10. Probability of seeing a skip list with more than 10 log n many levels is 1 over 1,000 to the 1,000 to the 9, making it 10 to the power 27. All right, it's 1 over 10 to the power 27. There's a chance that you'll see a skip list with too many levels. What's a complement expression? What is a complement event? If the first key doesn't want to participate in so many levels, nor the one, what's the chance of it? It's 1 minus the chance that somebody does participate in so many levels. It's 1 minus 1 over 10 to the 1 over 10 to the 27, making it an extremely unlikely event that you'll see such a bad skip list, or make it extremely likely that your skip list will be well behaved. Okay. Cool. I think that that's a good point to stop for today.